conflict. Not a word that most of us like to use very often. There's a lot of emphasis in our society on resolving or reducing or avoiding conflict. After a hard-fought election campaign, both the winner and the loser are eager to eliminate any suggestion of lingering bad feelings. The accent is on compromise, talking through problems, finding a middle ground, reaching a mutually satisfactory agreement. And of course, the theory of social choice, voting and distributing power, concerns fair methods for making socially acceptable decisions. But there's one area where conflict is out in the open, popular and exciting.
Third down and 14 now. We have a triple split on the right side for Harvard on the 48-yard line. White fires over the middle. Santiago wide open. He may go. He is that fast.
He's going to go.
Here comes no, he's in. He's in. Touchdown.
Goodbye.
48-yard pass play for a touchdown.
And direct competition doesn't have to be so dramatic. Both a chess master and a quarterback are proficient at a specialized form of conflict called a game. In mathematics, we use the idea of a game to describe a certain kind of decision-making situation. The hallmark of a game situation is that two or more participants, they might be individuals or teams or countries, have opposing interests. One side or player wants one thing, and the other player wants something different. In other words, conflict. There's another essential part of the idea of a game in mathematics. Each player, that's the standard term we'll use for a participant, has a set of options, alternative choices of action. We call these alternative choices strategies. And there's a branch of mathematics called game theory, which deals with methods for selecting the best strategies in a variety of situations.
The edge of math.
Hi.
Hi.
A little early, aren't you?
Yeah, well, I had my sushi tasting class today.
This week we join our typical couple, Henry and Lisa,
Oh, I got some
as they plan a business venture.
Thanks. Wouldn't it be neat to have like a Japanese setting with a lot of bamboo around?
But wouldn't that conflict with the rustic look we talked about? You know, the barn board on the outside and the exposed beams?
East meets west. I got it. What we'll do is we'll have the barn board on the inside, okay? And then we'll have bonsai trees growing on the outside. How about it?
Henry and Lisa are planning to open a health food restaurant in the hills outside San Francisco. Their plans are taking shape nicely, but one issue keeps coming up between them.
Do bonsai trees grow at high altitudes?
Sure. Mount Fuji's probably covered with them.
Great, because I talked to Pete Weller today, and he found us a beautiful piece of land high in the mountains. It's a great location for a restaurant.
Honey, you know I think that a high-altitude place is impractical. Besides, I get nosebleeds up that high.
This isn't the beginning of your let's put the restaurant in the middle of this city speech again, is it?
As a matter of fact, it is. The city's got something, I don't know, pulse, excitement. It's got atmosphere.
You call it atmosphere. I call it smog. It doesn't make any sense.
Consider Henry and Lisa as players in a game. The question is the location of their rustic but trendy health food restaurant, and their goals on this issue are in total conflict.
You know, you're talking really insane. You expect people to jump in their cars and drive for 3.5 hours to eat amongst your knotty pine and rustic atmosphere.
The people who spend $7 on a bowl of rice will drive 3.5 hours. Obviously, we can't agree on anything. I might as well call the realtor and tell him the whole thing's off. There won't be a restaurant.
Bad news for the Sprouts and Sushi crowd, unless Henry and Lisa can resolve this location problem.
Are we talking again?
Yeah. Pick a card. Whoever gets the highest one gets to choose where the restaurant goes.
Oh, honey, I don't want to fight anymore. But we can't just make a card game out of this. This is serious, okay? Let's look at the map again.
Again?
Yeah. Maybe we'll get some ideas.
If they're not going to get into the same fight they had in the kitchen, Henry and Lisa need a way to play this game.
Petrified Forest Road. That's the road that Pete says is ideal for the restaurant.
Yes, but look at this. Eureka Highway. That's where all the people go.
But there's tons of traffic on that highway.
Wow, yeah. Looky here. You take one of these roads that you like, and I'll take a highway, and where they cross, that's where the restaurant will be, okay? Okay, come on.
Well, that's not a bad idea.
Lisa's brainstorm turns this into a mathematically complete game. The choice of roads and highways make up Henry and Lisa's strategies, the alternative actions open to them. Well, we seem to have strayed pretty far from football and chess. But game theory and games are not the same thing. Sports and parlor games provided the key concepts, but game theory is a much broader mathematical construct, and it applies to exactly Henry and Lisa's kind of decision-making situation. Players with opposing interests and alternative actions open to them. Henry wants a high location for the restaurant, and Lisa wants a low one. Here's the lay of the land. There are 3 east-west roads and 3 north-south highways that run through the hills. To keep things simple, we'll call the roads A, B, and C. The north-south highways we can refer to as 1, 2, and 3. These are the same roads and highways arranged as a table, but it's not just an ordinary table. It's also the basic format for analyzing games. The partners have agreed, remember, that Henry will choose a road, so we'll put his name here, and Lisa will choose a highway. Our 2 players now occupy the traditional positions in game theory analysis. Henry is called the row player, and Lisa the column player. The list of roads make up Henry's choices. They are his strategies. And the list of highways are Lisa's strategies. At the intersection of each pair of strategies, say Road A and Highway 1, is a potential location, what we call an outcome of the game. Now, one of the fundamental principles of game theory is that we must quantify what each player will win or lose by playing the game. As we'll see, this so-called payoff might be money, or a military victory, a promotion, or perhaps a jail sentence. But we must be able to specify numerically what the players receive once a given outcome is reached. In this case, quantifying the payoffs is easy. Each payoff represents some actual altitude in feet. The whole arrangement, row and column players, strategies, and payoffs, is called a game matrix. How do our players think about this situation? Since they're serious about their preferences, they'll look carefully for strategies that bring them the best possible payoffs. These are basic rules of game theory. We assume a player is rational. He will choose a strategy that leads to his maximum benefit. And we also assume a player is competent. He won't make any mistakes in analyzing the available strategies.
See the light. Feel the heat.
With these ideas in mind, let's rejoin Henry and Lisa, who are settling this issue in a more relaxing setting. Using the materials at hand, Henry's built an incredibly accurate scale model to serve as a playing field for the location game.
A, B, and C.
Now, I had a chance to look it over, so why don't you take the restaurant and place it on the map where you think it looks best. I'm gonna go get some shells, and I'll be back in a minute. Go to work.
Wow. Well, it's pretty obvious. Right there, the lowest possible place. That's where I want my restaurant. Wait a second. If he picks Road A, and I'm on Highway 1, then I'm gonna wind up there, the highest point of them all. That's not gonna do it. Better check out Highway 3. Wait a second, every single one on this is too high. Even if he picks the lowest road of them all, it's still too high for my taste.
Lisa's figured out the right way to play this game. She can't just go for the lowest spot. She has to choose a highway that gives her a decent location, no matter which road Henry picks. What strategy will Henry use?
Well, I really like this road here because it's got this high spot. It's perfect.
What a surprise.
But you probably didn't give me this.
So Henry's got the idea too. Road B looks pretty good. He won't get stuck with any very low peaks there.
Well, how about Road C?
Road C is clearly a loser. All the points on C are lower than their neighbors on B.
Have you made up your mind?
Yes?
I've made up mine.
Okay.
Let's choose it on the count of 3.
Ready?
1,
2,
3,
go!
Both Henry and Lisa are trying to protect themselves. They're choosing in such a way that they minimize the amount of damage their opponent might inflict. We could call this tactic picking the best of the worst. Why would they take this approach? Henry, for example, could have chosen Road A. It has higher intersections at 6,000 and 10,000 feet. Maybe Lisa would choose Highway 1, hoping for the 2,000-foot location down here. Then Henry would luck out because the intersection of their strategies would be the 10,000-foot peak. But we stipulated that both players are rational and skillful. Each one, therefore, must assume that the other won't make any mistakes. Or to put it positively, your opponent will figure out any advantage that you can detect. Gambling on Road A, then, is a sure loser for Henry. What's especially interesting here is that both strategies lead to the same intersection, the 5,000-foot point at the junction of Road B and Highway 2. A common payoff point like this is called a saddle point. You can see where the name comes from by just looking at the map. It's the point that is both the highest of the low spots and the lowest of the high spots. When a saddle point exists in a game like this, both players should go for it. It's their best mutual outcome. If one player decides to ignore the saddle point, the other can be assured of doing even better. The optimal strategy for each player, therefore, is the one that produces the saddle point outcome. That's why it's considered the value of the game. This value, 5,000, together with the optimal strategies, Road B for Henry and Highway 2 for Lisa, constitute the solution of this game. The restaurant game, simple as it is, has a lot to tell us. First of all, each player found an optimal strategy. Second, for both players, the optimal strategy is what game theorists call pure. That means a strategy which they can easily identify at the outset and stick to throughout the game. And third, all the relevant facts are known to both players. That eliminates any need for secrecy. Both Henry and Lisa can announce their preferences and their strategies openly. Nothing they might say to each other should have any effect on the outcome of the game. So you can see that if a game has a saddle point, it's pretty important to discover it. And there's an easy technique for finding one. Let's look back at the game matrix. Remember, Henry is looking for the highest locations, but we start by identifying the minimum point in each row. Lisa prefers the lowest point, but her first step is to find the maximum entry in each column. Now we can easily pick out the maximum of the row minima, and down here, the minimum of the column maxima. If these values are the same, you've got it. This is the saddle point. The procedure we're using is called the minimax technique. In the restaurant game, we made all the payoffs positive to correspond to altitudes on the map. But this is only a slight variant of a fundamental type of game, the so-called zero-sum game. In a zero-sum game, a direct exchange takes place between the players. One player's gain is the other player's loss. Think, for example, of a bet in poker or the outcome of a battle. Because one player's loss is the other player's gain, the sum of the payoff values is zero. You find zero-sum games in situations of strict competition where the players' interests are directly opposed. Now, the minimax technique we used in the restaurant game will always identify the saddle point, if there is one, and therefore the pure strategy each player should use. But what if a pure strategy won't work? What should the players do then? Consider a different kind of game, one many of us play more often than we might care to admit. It's the game of trying to get away with parking in an illegal space. Will the police come by or not? Let's say you work here at City Hall. When you pull up in front, there are never any legal parking spaces available. So you have two choices. You can park illegally and have a leisurely stroll into work, or you can park further away at an outrageously overpriced lot. If you're tempted by the free but illegal street space, you're going to have to guess what the police are up to this afternoon. There are some facts you do know. The police are highly motivated to catch illegal parkers. They regard such criminal behavior as a direct flout to their authority. On the other hand, they always have a lot of paperwork to catch up on, and they'd rather get something done at the station house than walk the streets fruitlessly. This game matrix shows your two strategies: park illegally or pay in the lot. And the two strategies available to the police: go out on patrol or work at headquarters. Now, we need to specify numerically your payoffs for each of the possible outcomes. We'll measure these payoffs in dollars. Your first preference is to park illegally and get away with it. This is free parking. The cost to you is zero. Your next preference is to play it safe. You have to pay $8 at the parking lot, but at least you don't get a ticket. What you consider even worse is this: paying to park when the police don't go out on patrol. This is so galling that you consider it a double loss, minus 16. And this, of course, is your least preferred outcome. You go for it, and you find yourself staring at a $20 parking ticket. Now, we want to set this up as a zero-sum game. How do we do that? By assuming, for the purposes of this example, that your gain is the policeman's loss, and vice versa. That makes some sense, since you are adversaries in the game. You want to avoid a ticket, and the policeman wants to give you one. If we agree to model the parking game as zero-sum, we can determine the payoffs for the police from the matrix, just by changing the signs on the entries. In a zero-sum game, remember, each payoff for the column player is exactly the opposite of each payoff for the row player. The police most prefer to go on patrol and catch scofflaws like you.
When are these jerks gonna learn?
So they get 20 points for this outcome. Their second preference is for you to be so intimidated that you park legally in the lot while they get to catch up on filing reports at headquarters. Going further down their list of preferences, they're willing, but not too happy, to go out on the beat if that's what it takes to make you respect law and order. Finally, their worst outcome is to have the chief walk in while they're sitting around the station and ask what they plan to do about the car parked illegally out front.
Since it's anybody's guess where the police are going to be checking on any given day, and I'd love to park for free and kind of stroll into work, I'm going to grab this illegal spot.
Now, I see by the payoffs that you like to park illegally. So I'm gonna hit the streets on patrol.
The police can play this game, too. I'm gonna make him go on the beat. Meanwhile, I'll park in the lot. Teach him a lesson.
Of course, if they figure out we're gonna step up patrols, they're gonna park legally anyway. So I'll outfox them by going back to the office and diving into a stack of paperwork.
And I'm gonna park near City Hall.
Then I'll go out on patrol.
Then I'll park in the lot?
Then I'll do some paperwork?
And so on. Since both players are rational, each assumes the other is just as shrewd and just as determined to snare the maximum payoff. This kind of reasoning can only keep going in circles. The problem, as the Minimax technique reveals, is that this game has no saddle point. And that means trying to pick a pure strategy just won't work. If you settle on one course of action, parking illegally, say, the police will quickly catch on and know exactly what to do. So a pure strategy is no good. But there is a solution to a game like the parking game. John von Neumann proved it. In fact, he proved the existence of a solution for every zero-sum game. His discovery is called the Minimax theorem, and it's considered the fundamental theorem of game theory. Now, we already know quite a bit about what the theorem says. We've recognized that there are two categories of zero-sum games: games that have a saddle point and games that don't. For saddle point games, here's what von Neumann's theorem tells us. If the players follow their optimal pure strategies, they will reach the saddle point outcome, which is the best that each player can do. If a game doesn't have a saddle point, the Minimax theorem says there is a best average payoff for each player in the long run. But the optimal strategy for getting that payoff isn't pure. you have to choose different strategies in different plays of the game. The solution is therefore called a mixed strategy. The reasoning here is that if you rely on any one strategy, say parking near City Hall, the police will know what to do. So you have to mix your strategic choices. And the best policy is to mix them randomly, so that even you don't know what you're going to do until it's time to play. That way, you introduce the element of surprise and keep the other player off guard. After all, if the police let on that they're heading out on patrol, your decision would be pretty simple. And you shouldn't make it too easy for the police. It's not a good idea to loiter around the station house discussing in a loud voice where you plan to park.
You watch me tomorrow. I'm gonna grab that illegal spot right in front of City Hall.
Secrecy is an essential part of a mixed strategy game. So we can solve a game like the parking game, using the ideas of optimal mixed strategy and randomized choices. But you might think that we've reached something of a contradiction here. How can a choice be both optimal and random? Let's say that these red cards stand for parking illegally, and these black ones for parking in the lot. What the Minimax theorem says is that you can stack a deck in your favor. You can combine red and black cards in specific proportions, making up a deck that will give you the best strategy mix in the long run. Then each time you drive up, you're going to shuffle a deck, draw a card randomly, and follow that parking strategy. Here's how to figure out the right odds for loading the deck. We're going to put your expected payoffs on vertical axes and determine your optimal strategy mix from the horizontal axis. This axis, which runs from 0 to 1, represents the probability with which you should use your strategy of paying to park. When we've determined that proportion, then 1 minus p will give the frequency with which you should park illegally. First, consider the case where the police do go out on patrol. When p is 0, that is when you park illegally, your payoff is minus 20. When p is 1, and you go to the lot, your payoff is minus 8. As p varies from 0 to 1, your expected payoffs are shown on the line connecting minus 20 to minus 8. Now the case where the police do not patrol. When p is 0, that is when you park illegally, your payoff is 0, free parking. And when p is 1, you pay in the lot with a payoff of minus 16. Again, as p varies from 0 to 1, your expected payoffs trace a second downward sloping line from 0 to minus 16. The optimal p corresponds to the point where your two lines intersect, the highest point that can be reached on both lines simultaneously. You can see this point is about 5/7 of the distance along the horizontal axis. The precise number comes from solving the equations for the two lines. That means you should use the strategy of paying to park 5/7 of the time. And therefore, in this hypothetical case, you should park illegally 2/7 of the time. We configure the optimal strategy mix for the police in a similar fashion. The diagram shows that for every 4 times they go out on patrol, they should stay at headquarters 3 times. To pick your move for each play of the game, you should rely on random selection, but using a method that incorporates your 5-to-2 odds. For example, never leave home without your trusty spinner. If the needle lands in the green zone, park nearby. Otherwise, head for the lot. The red and green parts of the circle are in a 5-to-2 ratio. Of course, if you're properly high-tech, and you carry a portable computer around, you can use it to generate random numbers. That's how mathematicians actually carry out random selection in more complicated situations. Game theory has taken root and matured in areas far beyond von Neumann's pioneering investigation. For example, the parking game is a special case of a whole category of situations called inspection games. Another inspection game involves what's called material accounting. Nuclear power plants are required to account for their stocks of plutonium and other nuclear materials. It's the Nuclear Regulatory Commission's job to find out whether any plutonium has been stolen or diverted. But these inspections are costly, and they can be dangerous, so they can't be performed on a continuous basis. So the NRC is considering the use of game theory to select when and where to audit the nuclear materials accounts.
Can 88?
The Commission might, for example, classify nuclear power plants according to how much plutonium is reported missing.
1,477 grams.
The inspection teams could then use a mixed strategy, concentrating on plants with the most missing material while randomly inspecting other sites on a less frequent basis. The armed forces began to take advantage of game theory right after World War II. And a good example of the so-called decoy game comes from the 1950s, when atomic bombs were still rare commodities. Say the Air Force sent out a fleet of bombers. For each formation of 3 planes, it made sense to put one bomb in the middle plane, with the 2 outside decoys protecting it. But the enemy could also figure out that this was the most likely strategy. So the Air Force would randomize which plane actually carried the bomb, using a mixed strategy with proportions that favored the middle plane. This is a classic instance of the need to incorporate a surprise factor in strategic decisions. And don't forget, the IRS also knows about the inspection game. They use a mixed strategy to decide whether to audit your tax return. Mathematicians have also extended game theory into other complex applications in diplomacy, law, anthropology, even religion. Next time, we'll look at some examples of social and political games.